Hello and welcome to Controllers Tech. Today we will start a new series covering the ADC peripheral of the STM32 microcontrollers. We will cover different ways of reading the data from the analog devices throughout this series. This is the first video of the series, and today we will see how to configure the ADC, and how to use the polling mode to read the single channel of the ADC peripheral. I will use the STM32H750 development board throughout this series, but we will also see the configuration available in the F4 series and STM32F103 series MCUs. The STM32H750 and H743 development boards are available on the Controllers Tech store, so you guys can purchase these boards from there. Let's start the Cube IDE and create a new project. I am using STM32H750VBT6. Give some name to the project, and click Finish. Let's see the schematics of this board before proceeding forward. Here you can see that there is an external 25 MHz crystal available on the board. We will use this crystal to provide the clock to the board. Let's open the RCC configuration, and enable the high-speed external crystal. We will configure the clock in a while. Let's enable the ADC first. The channels 0 to 2 are not available, and we have channel 3 as the first channel here. The ADC can be selected in either differential mode, or the single-ended mode. We will cover the differential mode later in the series, so for now let's select the single-ended mode. Single-ended mode is basically the usual ADC we have available on other STM32 boards as well. Let's configure the clock now. This board has 25 MHz crystal, so set the value 25 here. I will use the PLL to run the system at maximum possible 480 MHz. Let's see the configuration available on the other STM32 MCUs. Here I am creating a dummy project on CubeMX. We will see the configuration for the F446RE. Let's enable channel 0 of the ADC. Here we do not have the option to choose the differential or single-ended mode. The ADC by default is using the single-ended mode, and we can't use different modes with this MCU. We will see the rest of the configuration in a while. Let's go back to our project. Here you can see the ADC clock is at 75 MHz right now. The ADC peripheral is using the clock from PLL2P, so we can modify it here to vary the clock fed to the ADC. You can even change the ADC clock source, but I will leave it to the default one. Now let's take a look at the F446 clock diagram. Here we don't have a separate clock data for the ADC. To know the ADC clock, we need to check the datasheet of the MCU. Here look for the block diagram, which basically contains the clock configuration. As you can see, the ADC1 is connected to the APB2 bus. If you look in the clock configuration, the APB2 clock is at 16 MHz right now. This makes the ADC clock also at the same frequency. Let's come back to our project now. We have enabled the ADC1 channel 3, and hence the pin PA6 is selected as the ADC pin. We will connect the potentiometer output to this pin. Let's configure the ADC now. The mode is set to independent mode, because this ADC is working independently right now. We can use the combined mode by enabling another ADC as well, but that will be covered in the future videos. The ADC has the configurable resolution, which can be set between 8 bits to 16 bits. The resolution configuration is also available on the F446, and here we have the options to choose between 6 bits to 12 bits. But all the STM32 MCUs do not have the option to choose the ADC resolution. Let's quickly see the configuration for the STM32 F103C8. Let's enable the ADC 1 channel 0. You can see we do not have the option to choose the ADC resolution. In such cases, you can refer to the reference manual of the MCU you are using. Here, if we check the ADC section, it is clearly mentioned that the MCU supports 12-bit resolution only. Basically, we can't choose the resolution, it is fixed. In today's video, I am choosing the 16-bit resolution for the ADC, and hence the ADC data will vary between 0 to 65535. Next is the scan conversion mode, which is used while using the multiple channels. We are using a single channel only, so let's leave it disabled. The continuous conversion mode enables the ADC to start another conversion as soon as the first conversion is over. Let's keep it disabled, so that we can see the difference. The discontinuous conversion mode is just the opposite of the continuous conversion mode. The end of conversion sets the flag when either a single conversion is completed, or a sequence of conversions is complete. For a single channel, we will leave it to single conversion only. I will leave the rest of these to default, we will see their usage in the future videos. The channel configuration can be found under the rank section. The channel is set to channel 3, as we have enabled only that. The sampling time is basically how long the ADC will take to sample and convert the data. We will cover the ADC sampling and conversion time in a separate video, let's set it to maximum for now. That is all the configuration we need. Let's check the configuration available in the F103C8. Here we have the data alignment, which is set to right align. Since the ADC has the resolution of 12 bits, the data can be only stored in the 16-bit variable. This data alignment basically sets whether to align the 12-bit data to the right of the array, or to the left of the array. Then we have the scan conversion, continuous conversion, and discontinuous modes as usual. Under the rank section, we have the same option to choose the sampling time. Now let's quickly see the configuration for the F446RE. Here we have the clock prescaler, which can be used to further divide the APB clock, so to reduce the clock fed to the ADC. For example, the APB2 clock is at 16 MHz right now, and if we use the prescaler of 8, the ADC clock will be reduced to 2 MHz. Then we have the option to choose the resolution, the data alignment, and the conversion modes. We have a new option here to enable the DMA continuous request. This is basically used when you want the DMA to continuously receive the data from the ADC peripheral. This option is not available in the F103C8 MCU, so there you can simply enable the DMA, and it will automatically fetch the data continuously. Here under the rank section, we again have the same options to choose the sampling time etc. We also have the option to choose the prescaler in the H750 MCU. For example, the ADC clock is at 15 MHz right now, and if we use the prescaler of 10, the ADC clock will reduce to 1.5 MHz. Alright, that is all we need for now. Click Save to generate the project. Here is the picture showing the connection between the potentiometer and the board. The VCC from the potentiometer is connected to the 3.3 volts, ground is connected to the ground, and the data pin is connected to the pin PA6. Alright, we will start with the polling mode to get the ADC data. Let's define a 16-bit variable to store the ADC data. We want to get the results continuously, so we will write the code in the while loop. First start the ADC. Then poll for the conversion to complete. We will wait 100 milliseconds for the ADC to sample and convert the result. Then read the ADC value and store it in the variable we defined. Finally, stop the ADC. Let's give a delay of 500 milliseconds between each call. We will also increment the count variable, so to make sure if everything is working alright inside the while loop. Alright, that is all we need to read the single channel ADC using the pole for conversion method. Let's build the project, and debug it to see the variable value. Let's add ADC value, and the count variables to live expression. You can see the variation in the ADC value, the fluctuations in the ADC values are normal. The count variable is incrementing every 500 milliseconds, so our while loop is working normally. Now let's slide the potentiometer to the other end. You can see the ADC value is incrementing as well. Now we are somewhere near the middle, and the ADC value is around 39,000. Let's keep sliding it towards the other end. Now we have reached the other end, the resistance of the potentiometer is maximum at this point, so is the ADC value. Since the resolution is set to 16 bits, the maximum value is 65,535, and it is what we got here. So the ADC value is varying as we slide the potentiometer, but we are not quite getting the value 0. At the lowest point, the ADC value is 1700. This is fine for now, as we can still refer to this as our lowest value. Some of the STM32 MCUs support the ADC calibration, we will talk about it in the future videos. Now let's assume that we want to map this ADC value to some specific range. We can use this map function, which I took from the Arduino source code. Call the map function after the ADC value has been captured. The output will be stored in the value variable. We want to map the ADC value, the minimum input value is 1000, the maximum value is 65,535, and we want to map it between 0 to 100. Actually the minimum input value should have been 0, but since we are only able to achieve 1700 with our ADC, I am setting it to 1000. Anyway, let's build and debug this project again. We will add the value variable to the live expression. You can see that the value variable is incrementing as I am moving the slider. It is towards the middle now, and the value is at 58. And when we move it towards the end, the value has reached 100. It is the maximum output value we set in the map function. So we can use the map function to get the output in terms of voltage, or in percentage resistance. So the poll method to read the ADC data is working fine. In this polling method, the CPU is blocked for the ADC operation and we cannot perform any other task during that time. The polling method does block the CPU, but this is good enough if you do not have any time-sensitive requirement from the ADC. We can use this method in combination with the RTOS to read the ADC values every few milliseconds. Today we will cover the interrupt mode, and the DMA mode to read the data continuously in the background, basically without affecting the other tasks performed by the CPU. We will continue the project where we left in the previous tutorial. Let's open the CubeMX to modify the project. Go to the ADC1, NVIC tab, and enable the interrupt for the ADC. Note that the continuous conversion mode is still disabled. We will first see how the ADC behaves with this being disabled, and then we will enable it later in the code itself. That is all I am changing, the rest of the configuration is same as the previous video. Alright, now inside the main function, start the ADC in the interrupt mode. Once the ADC finishes the conversion, an interrupt will trigger, and the conversion complete callback will be called. Inside this callback we will process our result. Here we will again read the ADC value, and store it in our variable. Then call the MAR function to amp this value in the range of 0 to 100. Let's change this minimum value to 1700, as this is what we got in the actual result. Let's build and debug this project. Keep in mind that the continuous conversion mode is still disabled right now. We will first see how the ADC behaves with it being disabled. I am setting one breakpoint inside this callback function. Alright, we have hit the breakpoint. This means the ADC has finished the conversion, and that is why the callback is called. We will read the value and map it in our specified range. Now resume the debugger. We do not hit the breakpoint again. This means that the ADC is not converting the results anymore. You can see the count value is increasing, so the while loop is working normally as it should. This is happening because we have not enabled the continuous conversion mode. We can still make it work by calling the ADC start function again inside the interrupt callback. Let's test this part. Alright, we keep hitting the breakpoint. This means that the conversion is happening continuously. Let's test the output with the slider. The count variable is incrementing every 500 milliseconds, so the while loop is working normally. Let's move the slider now. You can see the value variable is more responsible now. The value is increasing as we are moving the slider towards the other end. The interrupt is working fine, but this is not the way to do it. We do not need to start the ADC each time the callback is called. Instead, we can just enable the continuous conversion mode. Let's browse down to the ADC initialization code, and here change it to enable. Now the continuous conversion is enabled, so the ADC will automatically start the next conversion as soon as the first one is finished. Since we are using only one channel, the same channel will keep converting continuously. I have disabled this function here, so let's test the project again. The breakpoint is hitting again, that means the interrupt is triggering continuously. Let's remove the breakpoint and run the debugger again. We will now test it with the slider. You can see the value variable is changing as per the slider's movement. So the ADC is working fine in the interrupt mode also. The conversion is taking place in the background, and the while loop works as usual. Now keep in mind that if the ADC clock is very high, the interrupt will trigger at a higher rate, and this might make the while loop unusable. To prevent this, make sure that the ADC clock is at a reasonable frequency. Now we will see the use of DMA. Using DMA for a single channel is useless, as the conversion complete interrupt will trigger at the same rate as in the interrupt mode. So basically we do not have any advantage. I will demonstrate how to use it anyway. We need to enable the DMA, so open the CubeMX again. Now go to the DMA settings, and add the DMA. We want to enable the DMA for ADC1, the direction is from peripheral to memory, and the DMA priority is low. Select the DMA mode to circular, and make sure the data width is half word if you have selected the resolution higher than 8 bits. The circular mode allows the DMA to continuously request the data, whereas in the normal mode, the DMA will request the data only once and we need to start the DMA again for another request. We also need to change the data management mode also. Here we have the option for one-shot DMA mode, which is used when we want to receive the data using DMA only once. Whereas in the circular mode the DMA will continuously request the data from the ADC. The circular mode is used along with the DMA circular mode. We have another option available in the F446RE for the same. Here you can see the image showing the configuration for the F446. We have the option for continuous DMA request. So if you want to enable continuous data reception, this must be enabled. We do not have any option in the F103C8, so we will only enable the circular mode, and the data reception should be continuous automatically. Let's enable this continuous conversion mode, as it is needed for continuous data reception. That is all we need to configure, click Save to generate the project. In the main function, instead of the interrupt mode, let's start the ADC in the DMA mode. In the DMA mode, we need to provide the array where the converted channel data will be stored. Let's define a 16-bit array of 10 elements, which is basically 20 bytes in size. Since we are using a single channel, we will request the data for one element. Once the data is transferred by the DMA, it will trigger the conversion complete interrupt, just like the interrupt mode did. We can also request the data for all the 10 elements. In case of a single channel, the DMA will receive the data for 10 elements from the same channel, and it will then trigger a single interrupt for all 10 elements. We don't need the getValue function, as the converted data is already stored in the array. The received data is stored in the 0th element of the array, so we will use it to map the value within our specified range. We have got a warning here, and that is because the array is defined as 16 bits, while the function expects a 32-bit variable. Let's typecast it to the 32-bit pointer. Alright, let's debug this project. You can see the 0th element of the ADC value is varying, as the DMA is continuously updating the data in it. The count variable is incrementing every 500 milliseconds, so the while loop is working fine as well. Now we will move the slider. The value variable is updating as expected. The slider is on the extreme right, and the value is 100. Now the slider is on the extreme left, and the value is 0. So the DMA reception is working fine also. Let me quickly show what happens when we receive the data for all the 10 elements. We can take the average of all the 10 elements and then feed the result to the map function. But I will leave it as it is. You can see all the elements of the array vary in the similar manner. The DMA mode is more useful while converting multiple channels, and we will see it in the future videos. The rest of this video is exclusive to the Cortex-M7 based MCUs. While using the Cortex-M7 based MCU, we must enable the instruction and data cache. It is recommended by the street, as using these cache improves the system performance overall. The cache configuration is available in the Cortex-M7 section. Now we know that when it comes to cache, the DMA does not operate as usual. We will first see what issues there will be, and then how to solve them using different methods available. So I have only enabled the cache, the rest of the code is still unchanged. Let's build and debug the project now. You can see that the ADC value array is not updating at all. The count variable is incrementing as usual, so the while loop is working fine. The breakpoint inside the callback function is continuously getting the hit, that means the interrupt is triggering at the usual rate. It's just that the data is not being updated, and this is called the cache coherency. It will always happen whenever you try to use the DMA with cache enabled. I have already discussed it in my MPU related videos, which you can find in the Cortex-M7 playlist. These videos discuss the issues, and how to resolve them. You must check out these videos if you are using, or planning on using a Cortex-M7 based MCU. Anyway, I will summarize the solution here quickly. We need to invalidate the cache in the region where the ADC value array is located. To do so, we will first relocate this array to some other memory location. This can be done by using the section attribute. We need to define this ADC array section inside the flash script. Here I am relocating it to the address 30 million hex. It is basically at the start of RAM D2. Alright, let's build the project once. There seems to be some error in the relocation. Actually there should have been spaces here. Alright, everything seems fine now. Once you click on the main file, you can see the RAM D2 is now occupied with 20 bytes. If you check the memory detail, you can see that the array has been relocated to the RAM D2. Now the first method to deal with this issue is that we invalidate the cache each time before the DMA transfers the data. We don't have an issue of data loss in case of the ADC, so I will just invalidate the cache here. Call the function invalidateDataCache by address, and pass the address of the ADC value array, and the size of the array in bytes. Note that the cache must be invalidated before the DMA transfer starts, but since data loss is not an issue in ADC, we can afford losing the first data value. You can see the ADC value array is now updating as it should. If we move the slider, the value variable is also changing according to the slider's movement. So the DMA is now able to transfer the data, while the cache is still enabled. There is another method to deal with the cache, where we can use the MPU to set the memory region non-cacheable. Let's open the CubeMX, and open the Cortex M7 section again. Enable the MPU with privileged access only. Enable the MPU region, and set the base region address same as where we located the ADC value array. The ADC array is 20 bytes in size, but here we have a minimum size available as 32 bytes. So let's set 32 bytes. Set the access to all access permitted. Disable the instruction access, enable the shareability permission, disable the cacheability permission, and disable the bufferability permission. That is all for the MPU. Click Save to generate the project. I have commented out the invalidate cache command, so now we are completely relying on the MPU configuration. Here you can see the MPU related code has been generated at the end of the main file. Alright, let's build and debug the project now. You can see the ADC value array is updating as usual. So the DMA is working fine again, with the cache being enabled. I hope you understood how to use the interrupt and DMA to read a single channel of the ADC. Today we will start covering the multiple channels of an ADC. We can use polling mode and interrupt mode to read multiple channels also, but the ADC configuration varies across the devices. While I was testing it across different MCU series, I needed to make a lot of adjustments to make it work. Therefore I decided to cover multiple channels using only the DMA mode. Here the DMA mode does not mean that the conversion will continue forever, and the interrupt will trigger at a continuous rate. We can also use the DMA mode to only fetch the data when we need it, just like the polling mode. So this video is split into two halves. First we will see the use of DMA in the normal mode to read the multiple channels of the ADC. And then we will see the DMA in the continuous mode, where it will fetch the data continuously. Let's start the IDE to configure the project. Here I have already created a new project, ADC Part 3. The clock is configured to run at maximum 480 MHz. Let's go to the ADC1, and select channel 3 in the single-ended mode. You can see the pin PA6 got selected as the ADC1 channel 3 pin. I want to configure the nearby pins for the other channels. Pin PA7 is ADC1 channel 7. Here P in input P7 stands for positive input pin, and that is what we need for the single-ended mode. PC4 is ADC1 channel 4. This one is in yellow, as we still need to enable the single-ended mode in the configuration. PC5 is ADC1 channel 8 pin. Let's resolve the clock before we go ahead. Here the ADC peripheral is clocked by the PLL2P, which is clocked around 50 MHz. Here I am configuring it to run at 15 MHz clock. The ADC peripheral is also at 15 MHz, so I am using a prescaler of 10 to bring it down to 1.5 MHz. This is not a requirement, I just want to select low speed for the ADC, as there is no clock requirement for the potentiometers connected to the MCU. The ADC resolution is set to 16 bits. We need to enable the scan mode for multiple channels, but the cube does not allow us to do so. Let's scroll down to regular conversion mode. Here the number of conversions is still set to 1. Since we have 4 channels, let's set it to 4. The scan conversion mode is now enabled, and the cube will not allow us to disable it. The continuous conversion mode is used when we want the ADC to automatically start the conversion again for all 4 channels. But as I mentioned, we want to convert the data when we want, so let's keep it disabled for now. The end of conversion flag should be set once all the 4 conversions are over, so set it to the end of the sequence. The conversion data management mode should be now configured to use the DMA, but we haven't enabled the DMA yet, so we will come back here later. Now we need to configure the ranks for the channels. I am setting rank 1 for channel 3, so it will be converted first. Rank 2 is for channel 4, so it will be converted second. Rank 3 is for channel 7, so it will be converted third. And finally rank 4 is for channel 8, so it will be converted at last. You can set the ranks according to the sequence in which you want the channels to be converted. I am configuring the random sampling time, as there is no particular requirement for the potentiometers. Now let's go to the DMA section, and add the DMA for the ADC1. Keep the DMA in normal mode as we will use it only once. Also set the data width according to your ADC resolution. Now if we come back to the conversion data management, we have the options for the DMA mode as well. We want the DMA to run only once, so we will select one-shot mode here. Alright, that is all the configuration we need, so click Save to generate the project. In the meantime, let's see the connections. I have connected 4 potentiometers to the 4 pins of the ADC1. The ADC pins are connected to the middle pins of the potentiometers. All the potentiometers are powered with 3.3 volts from the MCU, and the ground pins are connected to the ground to the MCU. Now before we start programming it, let's see the configurations for other MCUs as well. Here I have the configuration for the F446RE. I have selected 4 channels of the ADC1. F446 does allow us to enable the scan conversion mode, so we will enable it. The continuous conversion mode should be disabled, and the end of conversion should be set at the end of all conversions. Now we will set the number of conversions to 4. And then configure the ranks for all the channels, just like we did in the H750. Now go to the DMA section, and add the DMA for ADC1. Make sure that the mode is set to normal mode, and configure the data width as per your resolution. Also make sure that the DMA continuous request is disabled, otherwise the DMA will keep transmitting the data from the ADC. That is all we need to configure in F446. Now let's see the configuration for the F103C8. Let's go to ADC1, and enable the 4 channels. It also does not let us enable the scan conversion mode. Scroll down to the number of conversions, and set it to 4. Now the scan conversion is enabled. You can configure the ranks for the channels, just like other MCUs. Make sure that the continuous conversion mode is disabled. Now open the DMA section, and add the DMA for the ADC1. The DMA should be in the normal mode, and make sure that the data width is half word. The ADC in F103C8 has a resolution of 12 bits by default, so data width needs to be half word, that is 16 bits. Alright, let's write the code now. Let's define a 16 bits array of 4 elements, we will store the data for the 4 channels here. Now inside the main function, start the ADC in the DMA mode. Pass the array that we just created, and we want to receive the data for 4 channels. Remember that we have configured the end of conversion flag to set when all the channels are converted. So the interrupt will trigger when all 4 channels are converted, and the conversion complete callback will be called. We can process the ADC data inside this callback, or we can also set another variable to indicate that the data has been received. Then inside the main function we will check if this variable is set, and then process the data here. Let's also increment the count variable every 500 milliseconds, to ensure that the rest of the while loop is working fine. Here I am calling the ADC DMA just once. Let's test this part first. The warning is for this array, as the function expects a 32-bit pointer here, but we will leave it as it is. Let's build and debug the project now. Let's set a breakpoint inside the callback function. Here you can see the breakpoint got the hit. That means the DMA has finished the data transfer of all the channels. You can even see the data for all the channels in the live expression. Now if we run the code again, this breakpoint will not hit. That is because the DMA is in the normal mode, and hence it only runs once. The count variable is incrementing every 500 milliseconds, so the while loop is working fine. Now we can start the ADC in DMA mode whenever we need to read the data from the potentiometers. The DMA will fetch the data from all the channels, and once done, it will stop automatically. We will test it by calling the DMA inside this loop, which runs every 500 milliseconds. Alright, let's debug the project again. The breakpoint is still set inside the callback function. We hit the breakpoint once. Now if we run the debugger again, we get another hit. The breakpoint is getting the hit every 500 milliseconds, that means the DMA is transferring data every 500 milliseconds. This is because we are repeatedly starting the ADC in DMA mode. Let's run the debugger without the breakpoint, and see if the data from all the potentiometers is being read. I am rotating the third potentiometer now, and you can see the third element of the array is increasing. I am fast forwarding the video. The value has reached the maximum 65,535, as the potentiometer is rotated to the extreme end. Now I am rotating it in the opposite direction, and the ADC value is now decreasing. I will leave it around 30,000. Now I am rotating the second potentiometer, and you can see the ADC value increasing. Similarly, if I rotate it in the other direction, the value starts decreasing. I will leave this one at around 20,000. Let's rotate the fourth one now. The ADC value is increasing, and it has reached the maximum. Now when we rotate it in the opposite direction, the value starts decreasing. I will leave this one at around 40,000. Finally we will rotate the first potentiometer. The ADC value is changing fine, just as the potentiometer is rotating. Let's leave this to around 10,000. Alright, all the channels of the ADC are working fine. So we can use the DMA mode to read the data when we want. It does not need to fire the interrupt at a regular interval. You can write a condition, and call the DMA function inside it, so the conversion will only take place when the condition is met. Or you can even use it with the RTOS, where a separate task can be assigned to start the ADC in the DMA mode. Today we will keep reading the multiple channels using the DMA, but we will do it in the circular mode. This way we would need to start the ADC in DMA mode just once, and the DMA will continue fetching the data from the ADC. I will continue where we left the previous project. Let's open the CubeMX to modify the previous project. Here the 4 channels are already selected, and the scan conversion mode is also enabled. Let's go to the DMA section, and select the circular mode for the DMA. In circular mode, the DMA will continue to transfer the data from the ADC. Now in the conversion data management mode, select the circular DMA. We also want the ADC channel's data to get updated, so enable the continuous conversion mode. This will allow the ADC to start another set of conversions as soon as the first set is finished. This way the DMA will always have the updated data to transfer from the ADC. Rest of the configuration will remain the same as we did in the previous video. Let's generate the code for our new project. Before we proceed ahead, let's see the configuration needed for the other MCUs as well. Here is the image showing the configuration for F446RE. We need to enable the continuous conversion mode, and also the DMA continuous request. Also in the DMA section, make sure that the DMA is configured in the circular mode. The rest of the configuration is the same as what we used in the normal DMA mode. Here is another image showing the configuration for F103C8. We just need to enable the continuous conversion mode, as we do not have the options for others. Now in the DMA section make sure that the DMA is configured in the circular mode. The rest of the configuration remains the same as we used in the normal DMA mode. Alright, let's build the project once. Since we are using the DMA in the circular mode, we do not need to call it again and again. We will call it only once in the main function, and it will keep fetching the data automatically. You can use the conversion complete callback to process the ADC data. Let's debug the project to see the working. The ADC value array is already added to the live expression, so let's run the debugger. You can see all the values of the array are varying very fast. This means that the DMA is able to fetch the updated data on each call. I am varying the potentiometer 3, and you can see the variations in the third element of the array. Now I am varying the potentiometer 2, and you can see the changes in the second element of the array. Similarly, other ADC values are also varying as per the potentiometers. The count variable is updating every 500 milliseconds, that means the while loop is executing at the normal rate as well. So we are able to read the multiple ADC channels using the circular DMA mode, where we just start the ADC once, and the DMA continuously fetches the updated results from each channel. Now since we are using the DMA in a Cortex-M7 based MCU, let's also discuss the issue of cache coherency. As per ST's recommendation, we should use the cache in a Cortex-M7 based MCU. This improves the overall system performance. So let's enable the instruction and data cache in the configuration here. When we use the cache along with the DMA, we face the issue of cache coherency, where the DMA reads the cached data instead of the actual data. To avoid this issue, we can configure the memory protection unit of the MCU, and set the data region non-cacheable. So let's enable the MPU in the default mode. I am going to relocate the ADC value array in the RAM D2, whose base address is 30 million hex. The ADC value array is 16 bits in size, and we have a total of 4 elements in it. Therefore the array size is 8 bytes in total. Although here we have 32 bytes as the least possible size, so let's select it. Now permit all the access, and disable all the access permissions. I have already explained in detail about the MPU configuration in 5 video series. You can check them out to understand the memory protection unit. Alright, now the first thing we need to do is relocate the ADC value array to another memory location. We can use the section attribute to do so. Here I am relocating it to the section ADC array. Now we need to define this location in the flash script. As I mentioned earlier, I want to relocate the buffer to the RAM D2, which actually starts at the address 30 million hex. Therefore we will link the section ADC array here. The rest of the code remains the same. We are starting the ADC in DMA mode just once, and then the DMA will keep transferring the updated data from the ADC channels. Let's build and debug the project. You can see the ADC value array is updating as it should. This means the DMA is able to fetch the updated data, instead of the cached one. So we are able to read the multiple channels of the ADC using the DMA. We started the ADC in the DMA mode just once, and then the DMA was continuously fetching the data from the ADC. The DMA was even able to fetch the updated data, so there was no issue of cache coherency while using the Cortex-M7 based MCU. Although there is no reason for us to not use the DMA while reading multiple channels, but since there are ways to do it, we will cover them. We will first use the method of discontinuous conversion mode to read one channel at a time. Later we will modify the pre-generated code itself, so that we can read any random channel at any point in our code. Here I have already created a project for this tutorial. The 4 channels are enabled, just like we did in the previous videos. The ADC clock is configured to run at 15 MHz. Let's configure the parameters now. I am using a prescaler of 10, so to reduce the ADC clock to 1.5 MHz. Now the first thing we will do is set the number of conversions to 4. This will automatically enable the scan conversion mode, which is a must for the multiple channels. As I mentioned, we will use the discontinuous conversion mode first. This mode is actually used to split a longer conversion queue to smaller queues. For example, if we have 10 channels to be converted, we can convert 4 channels at once, then another 4 channels, and then the last 2 at the end. But we can also use this feature to convert 1 channel at a time, therefore eliminating the need for the use of DMA. So enable the discontinuous conversion mode, and set the number of conversions to 1. This will split the queue of 4 conversions to 1 channel at a time. Also make sure that the end of conversion selection is set to the end of single conversion. We want to read the data from 1 channel at a time, therefore it is necessary. Set the conversion data to store in the data register itself. Now let's configure the ranks for each channel. Although we are using discontinuous mode to read a single channel, we will still not have the option to choose the channel to be converted. The channels will be selected as per the rank we configure here. Alright, I have configured the ranks and sampling time for all the channels. We are not using the DMA and the interrupt for this tutorial. We will simply use the polling mode to read the multiple channels. That is all we need to configure. Click Save to generate the project. Let's take a look at the configuration required for other MCUs. Here I have the configuration for the F103C8. I have already enabled 4 channels to be converted. Now the first thing we will do is set the number of conversions to 4. This will automatically enable the scan conversion mode, which is a must for the multiple channels. Enable the discontinuous conversion mode, and set the number of conversions to 1. Now you can configure the ranks for the channels according to the sequence in which you want to convert them. Let's take a look at the configuration required for the F446RE. Here again we will first set the number of conversions to 4. Now enable the discontinuous conversion mode, and set the number of conversions to 1. Set the end of conversion selection to single channel. Now you can configure the ranks for the channels according to the sequence in which you want to convert them. There is not much change in the configuration required in different MCUs. Alright, let's write the program now. Let's create a 16 bits array of 4 elements, to store the converted channels data. We will repeatedly convert the channels inside the while loop. Start the ADC first. Then poll for the conversion to complete. Here I am setting a timeout of 100 milliseconds. Now we will read the converted channel data, and store it in the 0th element of the array. Now remember that we should not stop the ADC, rather start the ADC again, poll for the conversion to complete, and read the converted channel data. We need to repeat the steps for the number of channels we are converting. The sequence in which we will get the results is based on the ranks we configured in the CubeMX. Once all the channels have been converted, stop the ADC. Let's also give a delay of 250 milliseconds before starting the conversion again. Note here that we cannot choose which channel is to be converted, we need to read the data in the same sequence as we configured the ranks in. This is how the 4 potentiometers are connected to the MCU. All the potentiometers are connected to the 3.3 volts, and the ground of the MCU. The middle pins of the potentiometers are connected to the ADC channel pins. Alright, let's build and debug the project now. I have added the ADC value array to the live expression. Let's run the debugger now. You can see that we are getting the data from all 4 potentiometers. They are changing every 250 milliseconds. I am going to fast forward the video now. I am rotating the first potentiometer, and you can see the variation in the 0th element of the array. I am leaving this value at around 50,000. Now I am rotating the second potentiometer, and you can see the variations in the first element of the array. I am going to leave the value at around 40,000. Similarly, rotating the third and fourth potentiometers varies the second and third elements of the array respectively. So we were able to read multiple channels using the polling mode, and without the use of the DMA. Although if you see the code here, there is no point of doing it this way. Since we have to read all the channels anyway, so why not simply use the DMA? We can stop the ADC after reading just 2 channels, so the rest 2 channels can be avoided, but if you want to get the data from the third channel, you still need to read the first 2 channels. As I mentioned earlier, the discontinuous conversion mode has an entirely different purpose. We can use this mode to read a single channel as we did just now, but practically this is not its purpose. I will make another video showing the actual purpose of discontinuous conversion mode. Now we will see another method to read the multiple channels in the blocking mode. Let's open the CubeMX to modify the project again. Let's disable the discontinuous conversion mode, as we are not going to use it anymore. The rest of the configuration will remain the same. The scan mode is enabled, as it is needed for multiple channels. Make sure the continuous conversion mode is disabled. The end of conversion selection should be set to the end of single conversion. This will make sure that the conversion complete flag is set after a single channel is converted. Let's generate the project again. I am going to refresh the project, so that the new configuration is visible. Let's comment out this part as we do not need it anymore. We need to copy the data from the ADC initialization function. This is where the channel configuration starts from. Let's copy the configuration for the rank 1. Now we will create a new function, ADC convert rank 1. Paste the channel initialization part here inside it. This code will basically configure the ADC channel 3 with rank 1. The sampling time is configured as per the CubeMX. After the channel has been configured, we will start reading the channel. To do so, start the ADC first. Then poll for the conversion to complete. Read the ADC value, and stop the ADC. Since channel 3 is configured with rank 1, we will get the data for channel 3 itself. Also remember that we have configured the end of conversion selection to the end of a single channel. Therefore the conversion complete flag will be set after each channel is converted, and hence we can get the data for each channel. We will create similar functions for the other channels as well. Let's rename this to rank 2. The rank 2 is configured for channel 4, rank 3 is for channel 7, and rank 4 is for channel 8. We also have different sampling time for all the channels. Comment out the pre-generated code for the channel initialization, so to avoid the conflict. Also copy this channel configuration structure definition, and paste it inside all the functions. Inside this function, we will just change the channel to channel 4, but keep the rank to 1. Also configure the sampling time as per the CubeMX configuration. The rest of the code for reading the ADC data remains the same. Now for reading the rank 3, we will change the channel to channel 7, keep the rank to rank 1, and change the sampling time as per the configuration. Finally for the rank 4 function, set the channel to channel 8. The rest of the code remains the same. Basically we have created different functions to read a single channel data for individual channels. Now in the main function we can simply call the particular function to read only one channel. We will test it by reading only rank 3, that is channel 7. When we were using the discontinuous mode, reading rank 3 was not possible until we had read rank 1 and 2. But with this method we should be able to read rank 3 without involving other channels. You can see that we are getting the data for rank 3. Let me vary the potentiometer 3. You can see the variations in the ADC value. This means that the rank 3 is being read properly. I am leaving the value at around 40,000, just remember this, as it will come handy when we read all the potentiometers together. Now we will do another test, where we will only read the rank 4. Here we are getting the value for the potentiometer 4. Now I am varying the fourth potentiometer, and you can see the variation in the ADC value. I am going to leave this value at around 60,000, just keep this in mind too. Alright, now we will read all 4 ranks at once. Let's build and debug the project now. You can see that we are getting the data for all 4 channels now. The rank 3 is at 40,000, and rank 4 is at 60,000. These are the same values which we set while testing the channels earlier. I am rotating the first potentiometer now, and you can see the variations in the first element of the array. Similarly, when I rotate the second potentiometer, you can see the variations in the second element of the array. So the code works fine, and we are able to read the individual channels at our wish. Basically you can call the individual function to read a particular channel data at any point in the code. This method is more practical than reading using discontinuous mode. If you want to read all the channels at once, better go with DMA. Today in this video we will understand the ADC sampling and conversion time. Basically we will first calculate the conversion time for the ADC channels, and then measure it on the scope. I will demonstrate the calculation and measurement as well. Also we will test the timing in both F446RE and H750 MCUs. Let's start the Cube IDE and create a new project. First we will test the F446RE. Give some name to the project, and click Finish. Let's start with the clock setup. Here we will bypass the high-speed clock source. The board has 8 MHz crystal, and we will run the system at maximum 180 MHz. Now let's go to ADC1, and enable channel 0. You can see the pin PA0 is selected as the ADC1 channel 0 pin. Let's configure the ADC clock first. As you can see in the clock configuration, we do not have a separate clock for the ADC. To understand where the ADC1 is getting the clock from, let's open the datasheet of the F446RE. Here you can find the clock information in this block diagram. As you can see here, the ADC 1, 2 and 3, all are connected to the APB2 bus. As per our clock tree, the APB2 peripheral clock is at 90 MHz, and this is going to be the ADC clock itself. My scope will not be able to measure such a high frequency, so let me reduce the clock here. We can use the APB2 prescaler to reduce the clock. It is still high, let's reduce the system clock itself. Alright, now our APB2 clock is at 4 MHz, and so is the ADC1 clock. We can use the ADC prescaler to further reduce the peripheral clock. I am going to use the prescaler of 6. The ADC resolution is set to 12 bits. This resolution also plays an important role in determining the conversion time. We will cover that in a while. Let's enable the continuous conversion mode. We will also use the DMA, as we want the conversions to be as fast as possible. Let's enable the DMA in circular mode, and also make sure that the data width is set to half word. Now enable the DMA continuous request to make sure DMA keeps on transferring the data from the ADC. End of conversion flag is irrelevant, as we are using a single channel. Now let's configure the channel itself. Here I am setting the maximum sampling time, that is 480 cycles. Here we have the formula to calculate the sampling and conversion time. The sampling time only depends on the sampling cycles we set in the channel configuration. But this time is irrelevant, as it only includes the time ADC takes to sample the channel. The conversion time is more relevant to us, as this is the time when ADC delivers us the value itself. As you can see here, the conversion time depends on the sampling cycles we set, the conversion time, and the ADC clock. Here the conversion parameter depends on the resolution we set. To find the conversion time taken as per the resolution, you can check the reference manual of the MCU. Here I have the manual of the F446RE. Inside the ADC section, look in the fast conversion mode. Here you can see data for the minimum conversion time available for different resolutions. The value 3 is the minimum sampling cycle we can set. So for 12-bit resolution, the conversion parameter is 12, for 10-bit resolution, the parameter is 10, and similarly for 6-bit resolution, the parameter is 6. The CubeMX shows 15 clock cycles, for 12-bit resolution, and that is because it is showing the minimum conversion time we can get. As we have 3 clock cycles as the minimum sampling time we can set here. The conversion parameter may vary with different MCUs as well. Let's check the manual of the F103C8. The ADC resolution in F103C8 is fixed to 12 bits, and it can't be configured to something else. As you can see here, the conversion parameter for this 12-bit resolution is 12.5 cycles. Whereas in F446RE, the conversion parameter for 12-bit resolution was 12 cycles. The parameter varies in different MCUs, so make sure you check the reference manual of your controller. Alright, let's do the calculation now. I have set the sampling cycles to 480, the conversion parameter for 12-bit resolution is 12. Now the ADC clock, the APB2 clock is at 4 MHz, and we are using the prescaler of 6. So the ADC clock is APB2 clock divided by 6. This makes the conversion time equal to 738 microseconds. We will test it in the scope later. Let's set pin PA1 as output, as we will use this pin to measure the conversion time. Go to the GPIO configuration, and set the output speed of this pin to very high. Alright, that is all we need to configure. Click Save to generate the project. Let's define a 16-bit variable to save the ADC conversion data. Now in the main function, start the ADC in the DMA mode. We will store the value in the variable we just defined, and there is just one conversion. When the DMA finishes the transfer, an interrupt will trigger, and the conversion complete callback will be called. Inside this callback we will toggle the pin PA1. Basically this pin is being used to measure how frequently the conversion is complete, and the callback is called. That is all. Let's build and debug the project now. I am using the logic analyzer to measure the pin timing. Let's run the debugger, and also capture the data on the analyzer. Here you can see the pin remains high and low for 738 microseconds. This is exactly the same time that we calculated for the conversion to complete. So the conversion completes every 738 microseconds, the interrupt is triggered, and the pin toggles. Our calculation for the conversion time was very precise. Now onwards I am going to modify this project in the CubeMX. Just for the demonstration, I am going to change the sampling cycles to 28 cycles. Let's modify the value in the formula too. We got the conversion time of 60 microseconds now. Let's build the project and flash it to the board again. You can see the pin is now toggling every 60 microseconds. This means that the calculation is correct, and we are able to calculate the ADC conversion time. Let's try it for multiple channels now. Here I am enabling 3 more channels in the ADC configuration. Let's set the number of conversions to 4. The scan conversion mode is now enabled. End of conversion flag is set to the end of all channels. Let's configure the sampling time for all the channels. I am going to choose a different sampling time for each channel. This will result in different conversion times for each channel. We will add the conversion time for all the channels, and compare it with the result we get. The rest of the configuration is the same. Let's generate the project again. We will now calculate the conversion times for all the channels, and add them together. The only change is in the sampling cycles. The rest of the parameters in this calculation remain the same. The total conversion time is 1.176 milliseconds. Let's see if we get the same with our code. Since there are 4 channels now, let's define an array of 4 elements. Also inside the main function, change the data length to 4. That's all we need to modify. Let's build and flash the project to the board. Let's see the timing on the analyzer now. You can see the time is exactly the same as we calculated, that is 1.176 milliseconds. So the calculation works fine with multiple channels too. The similar calculation works for all the STM32 MCUs, but I found some discrepancy while testing the H7 series MCU. We will see it, so let's create a new project for the H750. I am using a H750 VB-based custom board, just like I used in the previous videos. Give some name to the project, and click Finish. I am going to start with the clock setup first. I am selecting the external crystal to provide the clock. The board has 25 MHz crystal, and we will run the system at maximum, 480 MHz. Let's enable channel 3 of ADC1 in the single-ended mode. Let's go back to the clock configuration. We need to modify the ADC clock source to bring the ADC clock in our measurable range. Alright, the ADC clock now is 2 MHz, and this should be fine for our measurement. Let's go back to the ADC configuration. I am setting the prescaler to 2, so this will bring the ADC clock down to 1 MHz. The resolution is set to 16 bits. Let's enable the continuous conversion mode. We also need to enable the DMA, so let's add it in the DMA section. Make sure the DMA is in the circular mode, and also the data width is set to half word. Now set the end of conversion to the end of the sequence, and also set the conversion data management to the circular DMA mode. Let's set the maximum sampling time for channel 3, that is 810.5 cycles. The pin PA6 is selected as the ADC1 channel 3 pin, although I am not connecting anything to the pin. Let's set the pin PD8 as output, so to measure the toggle time. Go to the GPIO configuration, and set the output speed to very high. Let's do the calculation for the conversion time now. We need to find the details about the conversion parameter, so let's check the reference manual of the MCU. Here go to the ADC section, and you can find the details in the programmable resolution section. As mentioned here, for the 16-bit resolution, the conversion time is 8.5 ADC clock cycles. Let's put the values in our formula. We have selected 810.5 sampling cycles, 8.5 is the conversion parameter. The ADC clock is at 2 MHz, and we used a prescaler of 2. This will result in the total conversion time of 819 microseconds. Let's go back to the EE, and see if we get this time. The code will remain the same. We will first define a 16-bit variable to store the ADC data. Inside the main function, start the ADC in the DMA mode. Once the conversion is finished, an interrupt will trigger, and the conversion complete callback will be called. Inside the callback we will toggle the pin PD8. That is all we need to program. Let's build and flash the project to the board. You can see the toggle time is 1.638 milliseconds. This is not what we got in the result. We should have got the time around 819 microseconds, but this is not the same as being shown in the scope. Now if we divide the ADC clock by 2, we will get 1.638 milliseconds. I tested this across different sampling times and resolutions, but this division parameter remained constant. After doing a lot of digging in the reference manual, I found out the reason for the same. To understand this division factor, go to the ADC Common Register section. Here go to the Common Control Register. The bits 16 and 17 of the Common Control Register represents the clock mode. Under the clock mode, there are different sections for the devices with revision Y and with revision V. As per this statement, the ADC clock will have an additional divide factor of 2 for the devices with revision V. I have the MCU with revision V, and therefore this divide factor is applied to the ADC clock. Now what exactly is this revision V or revision Y? Here I have a picture showing the H750VB, and here you can see the letter V at the end, representing the revision V. Here is another picture of the same MCU, but with revision Y. So whether the divide factor will be applied or not, depends on the MCU revision you are using. As much as I have tested it, the same is valid for other H7-based MCUs as well. I have not tested the devices with revision Y, but as per the reference manual, they should not have this divide factor. If you guys have the H7-based MCUs with revision Y, please let me know the result in the comments below. Other than this divide factor, the rest of the things are just as we have seen in the F446. In today's video we will cover the external trigger source for the ADC. Basically we will use one of the timers to control the sampling rate for the ADC channels. I am going to use the same STM32H750 custom development board which I have used in previous videos as well. Let's see the connections once. This is how the potentiometers are connected to the dev board. All the potentiometers are powered with 3.3 volts from the board itself. The outputs from the potentiometers are connected to the 4 channels of the ADC1. We will configure these channels in the Cube MX. I have created a new project for this tutorial. Right now I have configured only one channel of the ADC1. Here you can see the pin PA6 is configured as the ADC pin. Let's configure the parameters now. ADC clock is not an important parameter for this tutorial, so let's set the prescaler to 1, so as to generate a fast clock. The ADC resolution is set to 16 bits. It is very important to keep the continuous conversion disabled. If this is enabled, the ADC will start the next conversion as soon as the first one is finished. If that happens, the conversion will go on continuously, and we won't be able to control the sampling rate. End of conversion is set to single conversion as we have enabled only one channel. The conversion data should be stored in the data register only. There is only one channel for now, and I have set the minimum sampling time for it, that is 1.5 cycles. Now let's check the available external trigger sources for the ADC. If you browse through this list, we have various timers listed here. Choosing the trigger out event of any timer is a better option. This trigger event is easy to configure in the timer. I am choosing the timer 1 trigger out event. Also the trigger edge is set to the rising edge. Before we configure the timer, let's check the block diagram in the H750 datasheet. This diagram helps us determine the clock structure of the MCU. Here you can see the timer 1 is connected to the APB2 bus. Here in the clock diagram you can see that the APB2 timer clock is running at 240 MHz clock. Keep this in mind while we configure the timer 1. Set the clock source as internal clock. Since the timer is connected to APB2 bus, the timer clock is also at 240 MHz. I am setting the prescaler to 24,000, this will reduce the timer clock to 10 kHz. Now if we use the auto reload value of 1000, the timer clock will reduce to 10 Hz. We will use this frequency to sample ADC channel. Here at the bottom you can see the trigger event selection. There are 2 of them, but I am using the first one. Let's set the trigger to update event. Doing this will generate an event each time the timer's counter is reset. This event will trigger the conversion start in the ADC. Here you can see there are 2 trigger out sources available from timer 1. I have configured the first one, therefore the same is set here. We will read the ADC in interrupt mode, so let's enable the ADC interrupt in the NVIC tab. Let's set the pin PA1 as output, so that we can measure the sampling rate on the scope. Alright, that is all we need to configure. Let's generate the project. We will write the main file now. Let's define a 16-bit variable where we will store the value obtained from the ADC. Inside the main function, first start the timer 1 base mode. Then start the ADC in the interrupt mode. Once the ADC conversion is finished, an interrupt will trigger, and the ADC conversion callback will be called. Inside this callback we will read the ADC value, and store it in the variable we just defined. Now toggle the pin PA1, so that we can see the frequency of this loop on the scope. That is all, let's build the project now. We do not have any errors, so let's launch the debugger. I have added the variable ADC value to the live expression. You can see the ADC value is updating every 100 milliseconds. Well, we cannot be certain about 100 milliseconds, but we have set the timer frequency to 10 Hz, therefore it must be updating every 100 milliseconds. We will confirm this on the scope in a while. I am now rotating the potentiometer in one direction, and you can see the value is reducing. Now I am rotating it in the other direction, and the value is increasing. The ADC resolution is 16 bits, therefore the maximum value obtained here is 65,535. Let me leave it around 60,000. Alright, let's see the toggling frequency of pin PA1 on the logic analyzer. Here you can see the pin toggles every 100 milliseconds. This means that the ADC conversion complete callback is being called every 100 milliseconds. So we were able to achieve the ADC sampling rate of 10 Hz with the external trigger selection mode. The configuration remains the same across other STM32 devices as well, therefore I am not showing it for others. Now we will see the same for multiple channels. Let's open the CubeMX again. Here we will enable 3 more channels for ADC1. Now go to the number of conversions, and set it to 4. The scan conversion mode is automatically enabled. Make sure that the continuous conversion mode is disabled, or else the ADC will start the next sequence of conversion again as soon as the first one is finished. This way we won't be able to achieve the desired sampling rate for the ADC channels. Let's configure the channel ranks. I am setting the minimum sampling time for all the channels. Alright, since we are using multiple channels, we need to use the DMA to transfer the data. Let's go to the DMA tab, and enable the DMA request for ADC1. Make sure the mode is circular, and the data width is configured according to the ADC resolution. Since we are using DMA to transfer the data, the conversion data management should be set to DMA circular mode. Also we are converting 4 channels now, so the end of conversion should be set to the end of sequence. This way the interrupt will trigger only when all the channels have been converted. This configuration is the same as what we did for the multiple channels using DMA mode, except that the continuous conversion mode is disabled this time. Now finally we need to configure the MPU for the Cortex-M7. Enable the instruction and data cache. Now enable the MPU in the default mode. I have already explained it in multiple channels using DMA video. Basically we will relocate the data buffer to another SRAM, which is located at the address 30 million hex. Here we are simply configuring that region as non-cacheable. That is all we need to configure. Let's generate the project again. Here is the article about the ADC multiple channels using DMA. Here is the part explaining the configuration for the Cortex-M7. Let's copy this buffer definition, and we will paste it in our code. Also we need to create a section in the Flash script file. Now in the main function, after starting the timer, we will start the ADC in the DMA mode. The data will be stored in the ADC value array, and we want to convert 4 channels. When all the channels have been converted, the conversion complete callback will be called. We do not need to read the value, as it is already stored in the array. Here we will simply toggle the pin PA1. That is all we need. Let's build and debug the project. Here you can see all the 4 channels are updating frequently. To confirm the sampling frequency, we can check the PA1 on the logic analyzer. Here you can see the pin remains high and low for 100 milliseconds, which means that the callback is being called every 100 milliseconds. This means that the sampling frequency is indeed 10 Hz. The first potentiometer is set at 60,000. I am rotating the second potentiometer to go around 50,000. Then I am rotating the third one to go around 30,000. and the fourth one is around 40,000. So the ADC channels are responding fine, and the sampling rate is at 10 Hz. Let me demonstrate a different sampling rate now. Here is the timer 1 configuration, and this is the auto reload value we set at 1000. I am changing this value to 10,000. Doing so will reduce the timer clock to 1 Hz, and this will be the sampling frequency for the ADC. So the data will update every 1 second, and the pin PA1 will also toggle at this interval. Let's see the result in the debugger. You can see the channel data is updating every 1 second now. Let's check the pin PA1 on the analyzer. You can see the pin remains high and low for 1 second. So the conversion complete callback is being called every 1 second, and therefore the sampling frequency is 1 Hz. So I hope you understood how the sampling frequency of the ADC can be controlled. Let's quickly see if there is any change in configuration needed for other MCUs. Here is the configuration for the F103C8. Under the external trigger source, we have the events from different timers. You can see the trigger out event from timer 3, so you can use it. We can also use the event from capture compare mode, but this requires a little more understanding of the timer's operation. Since the trigger out events are available in every MCU, we don't really need to look into the capture compare events. But if you want, I can make another video explaining the usage of capture compare mode to control the sampling frequency. Make sure the continuous conversion mode is disabled while using the external trigger source. In today's video we will cover the ADC injected channels. We will see the difference between the regular channels and injected channels, how to configure the injected channels, and what are different working modes in injected channels. I am using the same H750 based custom development board for this tutorial, which you can purchase from the controller's tech store. Here I have already created a new project for this video. This is basically a multiple channel reading with circular DMA mode. Here you can see 4 different ADC channels have been configured, just like we did in the previous videos of this series. The continuous conversion mode is enabled, so the conversion for the sequence of 4 channels will continue as soon as the first sequence is finished. The DMA is enabled in the circular mode. I have configured 4 channels in the regular mode, and the sampling time for all the channels is set to maximum. I have also set the pin PA1 as the output, so that we can measure the conversion rate for these channels. Here in the main function, we start the ADC in the DMA mode. Once the conversion for all 4 channels is finished, an interrupt will trigger and the conversion complete callback will be called. Inside this callback we will toggle the pin PA1. This will give us the time taken by these 4 conversions to finish. Since we are using DMA, a Cortex-M7 based processor, we are relocating the buffer to a separate RAM. The relocation is defined in the flash script file, and the MPU is already configured in the CubeMX. I have already covered all this in the circular DMA video. Alright, we will first test this part, so that we can see the conversion time for these channels in the continuous mode. I am going to measure the pin toggling time on the logic analyzer. Let's run the debugger now. Here you can see the data from 4 channels is being shown in the live expression. Let's capture the pin PA1 on the analyzer. You can see the pin remains high and low for approx 1.02 milliseconds. This time remains almost constant for each toggle. So we can deduce that the total time taken by ADC to convert 4 channels, along with the DMA to transfer the data, is around 1.02 milliseconds. Remember this time, as we will compare it with when we enable the injected channels. Now let's see the ADC injected channels. Before we configure the injected channels, let's understand what it is. Here I have the reference manual of F446RE, and I have highlighted the important points regarding the injected channels. As mentioned here, the regular group can have up to 16 conversions, whereas the injected group can have up to 4 channels. This number can vary depending on the microcontroller, so do check the manual of your controller. The single conversion mode works in the similar way for both regular and injected mode. We can convert the group of channels once. The regular channels can be used in the continuous conversion mode, whereas the injected channels cannot be converted continuously. Although there is an exception when the injected channels are being used in the auto-injection mode. We will see this in a while when we will cover the auto-injection mode. Let's see the types of injections we have. The first one is the triggered injection. As the name suggests, in this mode the conversion is started either by the software, or by the external trigger. In triggered injection mode, if the injected conversion starts while the regular conversion is going on, the regular conversion is reset, and the injected channels are converted once. Then the regular conversion is resumed from the channel where it was interrupted. But if it is the other way around, the regular event occurs during an injected conversion, the injected conversion is not interrupted, and the regular sequence is executed at the end of the injected sequence. Basically the injected channels have higher priority, and it can interrupt the regular conversion sequence. The next mode is auto-injection. In this mode, the injected group is converted at the end of the regular group. We have discussed above that the injected group can be converted continuously in this mode. Let's assume that we have 6 regular channels in the continuous conversion mode, along with 3 injected channels in auto-injection mode. The 6 regular channels will be converted first, and then the 3 injected channels will be converted. This sequence of conversion will continue forever. So basically we will be converting a total of 9 channels. Although the interrupts will trigger separately for the regular group, and the injected group. We will see working of both modes now. Let's configure the Cube MX again. I am going to enable 2 more ADC channels, which we will use with the injected mode. The channel 18 needs to be manually enabled from here. Now scroll down to the injected conversion mode, and enable the injected conversions. The number of channels are going to be 2. We will use the triggered mode first, and the trigger source is going to be the timer 1 trigger out event. This is when the discontinuous mode is used for the injected channels. Let's configure the ranks for these injected channels. I am setting rank 1 for channel 18, and rank 2 for channel 19. Both channels are configured with least sampling time, that is 1.5 cycles. We will use the injected conversion in interrupt mode, so let's enable the ADC interrupt in the NVIC tab. We have configured the timer 1 as the external trigger source, so let's configure the timer 1 now. Let's set the internal clock as the clock source for the timer 1. The timer 1 is connected to the APB2 bus, which is running at 240 MHz. We have already discussed this configuration in the previous video, so I will cover it in short this time. I am going to use the prescaler of 2400, along with the auto reload of 1000. This will bring down the timer clock to 100 Hz, so the trigger time will be every 10 milliseconds. Set the trigger event selection to update event. Let's also set the pin PA2 as output, so that we can measure the trigger duration on the scope. That is all we need for now. Click Save to generate the project. Let's define a new array to store 2 16-bit data. Inside the main function, we will start the timer 1 in base mode. Then start the ADC injected conversions in the interrupt mode. Once the conversion is finished, an interrupt will trigger and the injected conversion complete callback will be called. Inside this callback we will first set the pin PA2. Then we will read both the injected channels, and store the converted values in the array we defined. The injected channels have separate data registers for each rank, therefore we can read them in sequence, and still get the results for both the ranks. This is one of the major advantages it has over the regular channels, where there is only one data register for all the ranks, and hence we need to use the DMA to read multiple channels. Finally, reset the pin PA2. This will give us an idea about how frequently the callback is being called, and how much time is taken to read the converted values. Alright, let's build and debug the project now. I have already added both the arrays in the live expression. Let's run the debugger now. You can see the injected channels are updating very frequently, and we are getting the data for all 6 channels. Now I am going to vary the potentiometer on channel 18, and you can see the ADC data varying. Now I am varying the potentiometer connected to channel 19. So the data is updating fine, and the injected channels are responding to both the potentiometers. Let's see the pin toggling on the logic analyzer. Before we start the capture, note that the high and low time for the pin PA1 is around 1.02 milliseconds. Alright, we have the toggling data for both the pins now. The spikes in the second row indicate the points where the injected conversion was done. You can see the high and low time for the pin PA1 is the same as what we got without the injected channels, that is 1.02 milliseconds. But this changes when it crosses with the injected channel. Now the time is 1.05 milliseconds. You can see it again at this point, the low time for the pin PA1 is 1.05 milliseconds. On the other hand, the duration between the spikes is 10 milliseconds. The timer 1 trigger updates every 10 milliseconds, therefore the injected conversion takes place every 10 milliseconds. You can see this time is constant between each spike, therefore the injected conversions take place at a constant rate. If we zoom into the spike, we can see that the pin remains high for 333 nanoseconds. This is the time taken by the MCU to read both channels, before resetting the pin again. Because of the injected conversion triggering every 10 milliseconds, we see the conversion time for the regular channels getting increased once every 10 milliseconds. This proves that the injected conversion is prioritized over the regular conversion, hence the duration for the regular conversion is increased. So we saw 2 advantages the injected channels have over the regular channels. First, the injected channels are prioritized, therefore it can interrupt the regular channels in operation. Second, the injected conversions have separate data registers for all the 4 ranks, therefore we can read the values for individual ranks while using the multiple channels. We have seen how the triggered mode works for the injected conversions. Now we will see the auto-injection mode. Let's change the injected conversion modes to auto-injection. You can see that all the triggers have been disabled automatically. We have discussed it earlier. In auto-injection mode, the injected group is converted at the end of the regular group. Also, the injected group can be converted continuously, but the triggers are not allowed in this mode. That is all. Click Save to generate the project again. The code will remain the same, so just build and debug the project again. Here the live expressions show the similar behavior. We have the data from all 6 potentiometers, and it is constantly varying. But how this data is being obtained, can be found in the logic analyzer. Let's capture the pin toggling data again. You can see that the spike is now at the end of each toggle of the pin PA1. This means that the injected channels are converting at the end of the regular channels. The toggle indicates that the regular channel has finished conversion, and the callback is also served. Immediately after the toggle, you can see 2 spikes in the pin PA2. These are because we are converting 2 injected channels, and therefore the interrupt is being called twice. So this is how the auto-injection works. The injected channels are converted after the regular channels. If there are a total of 16 regular channels and 4 injected channels, using the auto-injection mode we can convert a total of 20 channels. If the continuous conversion mode is enabled, these 20 channels will convert continuously. Today we will see how to use the oversampling to increase the resolution of the ADC. Oversampling can be incorporated to increase ADC resolution past the currently available number of bits. This can help reduce the cost in building a system, by utilizing lower resolution ADCs to oversample a signal, and obtain a higher resolution result. You can read more about the oversampling in the application note, AN5537. I will just cover some important points mentioned in the hardware sampling section of this note. I have got a new device from Active Firmware Tools. This is a logic analyzer cum debugger, which can be used as an oscilloscope and as a firmware debugger too. I will use this device to generate the sinusoidal signal, which the STM32 will read. Then the STM32 will send the digital data to this device, which will be graphed on this device itself. I am still testing this device, and once I finish exploring it, I will make a video about it too. I will leave the link to the product in the description, do check it out if you are interested. I am using Nucleo L496 for today's video, and here is the connection diagram. The output pin from the Active Pro carries the sinusoidal signal, and it is connected to the pin PA3 of the board. This is basically the ADC pin. This output pin is also connected to the analog input of the Active Pro, so that we can visualize the sinusoidal signal. The debugger can be connected using the SPI, therefore these two pins are used for half-duplex SPI connection. Alright, let's start the Cube IDE and create a new project. I am using the Nucleo L496 development board for this video. My regular boards F103C8 and F446RE do not support the oversampling. The H750 do support it, but things are very straightforward in it. Therefore I decided to use this L496, as it will help us understand the topic more clearly. Let's start with the clock setup first. This board does not have an external high-speed crystal, so let's use the multi-speed internal RC oscillator itself. I will run the system at maximum 80 MHz clock. Alright, let's enable the ADC now. I am using the pin PA3 of the MCU, which is ADC1 channel 8. Let's configure channel 8 in single-ended mode. Before we configure this further, let's go back to the clock configuration. The ADC is running at 40 MHz, but I need it to run at 64 MHz for better explanation of the oversampling. So let's configure the PLL to make it 64 MHz. Alright, the ADC clock is at 64 MHz now, and if we use the prescaler of 64, it will come down to 1 MHz. Let's configure the resolution to 6 bits for now, so that we can understand the importance of higher resolution later. I am only using one channel in the continuous mode, so let's enable the continuous conversion mode. We also need to enable the DMA continuous request, but let's configure the DMA first. Here I am configuring the DMA in the circular mode, so that the data can be transferred continuously. Note that I am setting the data width to half word, that is 16 bits, even though the ADC is configured with 6 bits resolution. I am going to change the resolution later, so this setting will remain unchanged. Now enable the DMA continuous request. We will not configure the oversampling for now. Let's configure the sampling time for channel 8. Here is the reference manual of the L496. Under the ADC programmable resolution you can see the sampling time for different resolutions. For the 6 bits resolution, the ADC takes 6.5 clock cycles to convert the result. Now if we use the sampling time of 47.5 cycles, the total time taken by ADC to sample and convert the result would be 54 microseconds. We will see this on the analyzer. Let's set the sampling time of 47.5 cycles. As I mentioned, I am using the Active Pro Analyzer and Debugger to debug this application. The device can work with the SPI, so I am configuring the SPI in half-duplex mode to transmit the data to the debugger. I am going to use the DMA for data transfer. I am also going to toggle a pin, which will help us measure the ADC conversion time. Therefore the pin PD7 is configured in the output mode. Alright, that is all the configuration we need, so click Save to generate the project. Let's build the project once. We will first define a 16-bit variable to store the ADC raw data. Now inside the while loop, start the ADC in the DMA mode. The converted data will be stored in the variable we just defined, and we are converting only one channel. Once the ADC finishes the conversion, an interrupt will trigger, and the conversion complete callback will be called. Inside this callback, we will toggle the pin PD7, and then set the variable done to 1. Now inside the while loop, we will check if the variable is done is set to 1. If it is, we will send the ADC value to the debugger, and then reset the variable to 0, so that this loop can only run when the ADC has finished conversion. Alright, let's build and flash the project to the board. This is the software for the Active Pro Debugger and Logic Analyzer. This is the output section, and here I am configuring channel 1 to output the sine wave. I am setting the maximum voltage to 1.1 volts, so that there will be less variation in the voltage. Here you can see the data sent by the STM32, the toggling pin PD7, and at the bottom we have the feedback from the Active Pro itself. Let's see the toggle time first. You can see the pin toggles every 54 microseconds, which is exactly the same as we calculated. The maximum voltage is reaching around 900 millivolts, which is less than expected. It might be due to some wiring issue, but let's continue anyway. Now since we are using 6 bits resolution, there are less number of values available for the voltage variation. Therefore you will see this line remains horizontal for a lot of the time. In fact the voltage at this point is around 168 millivolts, whereas it is around 268 millivolts at the end of the horizontal line. So for almost 100 millivolts, the line remained horizontal at the value 2. Similarly, the line is horizontal for other values as well. The STM32 reference voltage is set to 3.3 volts by default, therefore for the 1.1 volts the maximum value we can get is 1/3 of the maximum value. So we have seen how in the low resolution, the ADC is not able to differentiate between small voltage variation. Let's configure the resolution to 12 bits now. We will keep the other configurations unchanged. Now we are using 12 bits resolution, so the conversion time will change. The ADC takes 12.5 cycles to convert the 12 bits resolution. If we keep the sampling time the same as the previous value, we should now get the result every 60 microseconds. Let's generate the project again. We will keep the code unchanged, let's build and flash it to the board. Let's run the debugger again. Here you can see the flat lines are gone now. Since there are more values available for the ADC, it can show variation for even small changes in the voltage. The pin toggling time is 60 microseconds, which is the same as we calculated. I have fixed the wiring now, and here you can see the maximum value we are getting is around 1350. As I mentioned, the STM32 reference voltage is 3.3 volts by default, and therefore the input voltage of 1.1 volts is equivalent to the 1365. We are getting almost the same value here. Our curve looks better than before now, and the ADC values are updating as per the analog signal. Now let's imagine I want an even higher resolution, higher than 12 bits. This is where the oversampling comes in. Here we have the option to enable the oversampling, so let's enable it. The oversampling ratio decides how many samples we want for each trigger. Let's take a look at the application note again. This note is specific to STM32L4 devices, but the same logic works for all the STM32 devices as well. There are only a few differences, and we will see them too. We know that the number of bits increases after oversampling. In some of the STM32 devices, the oversampling engine keeps the 16 least significant bits after the shifting, and rounds the result of the removed bits. The size of the ADC data register in such devices is 16 bits, therefore a higher number cannot be stored into this register. But devices like the H750 have an ADC data register, which is 32 bits wide, therefore we can store even higher resolution results in it. We will see it at the end. Here in the Cube MX, you can see the oversampling ratio of 32 to 256 is grayed out. Let's understand it in the application note. This formula here gives the bit depth after the oversampling. Here X represents the bits on which the samples are accumulated at, N represents the oversampling ratio, and M denotes the bit shift. For example, if we accumulate the samples at 12-bit resolution, and the oversampling ratio is set to 32 without any bit shift, the resulting resolution will be 17 bits. Now as I mentioned, the ADC data register in L496 is only 16-bit wide, hence storing 17 bits in the data register is not possible. Therefore we need to shift the bit by 1, which will result in 16 bits resolution. Similarly, if we use the oversampling ratio of 64, it will result in 18 bits resolution. Therefore we need to shift the bits by 2, which can result in 16 bits resolution. As you can see, these ratios are blocked right now. But if we enable 1-bit shifting, the ratio of 32 gets unlocked. Similarly, if we enable 2-bit shifting, the ratio of 64 gets unlocked. So without any bot shifting, an oversampling ratio of 2 will result in 13 bits, 4 will result in 14 bits, 8 will result in 15 bits, and a ratio of 16 will result in 16 bits. At this moment, if I shift the bits by 4, the resolution will be 12 bits as shown in the calculation. But I am keeping it at 16 bits. Also note that I am not modifying the ADC clock. We will first see how it works out with this configuration itself. There are no changes required in the code. Let's build and flash the project to the board. Here you can see now we have the maximum values ranging up to 19,500. Let me change the output voltage to 3.3 volts here, and we will capture the data again. Now we are getting the maximum values of around 62,000. This means the resolution is now 16 bits. You can also observe the curve is smoother than before, and we have less jitters in the data. Let's check the ADC conversion time. The time is around 960 microseconds, although we were getting 60 microseconds in 12 bits resolution. So what happened? Like I mentioned, for the oversampling ratio of 16, the ADC will take 16 samples for each trigger. Basically the conversion starts as soon as the previous conversion is over. For a single sample, the ADC is configured to take 60 microseconds, and therefore for 16 samples, it will simply take 16 times the more time, hence 960 microseconds. In simple words, the oversampling by a ratio of 16 reduces the sampling frequency by a ratio of 16. So to maintain the sampling frequency at the previous rate, we need to either increase the ADC clock by 16 times, or reduce the channel sampling time, so that the resultant change would be the increase in sampling frequency. I will simply reduce the prescaler to increase the ADC clock. Since the oversampling ratio is 16, I am reducing the prescaler by 16 times, so that the ADC clock can increase 16 times. Alright, now we will test the project with this configuration. Let's capture the data again. You can see we still have the 16 bits resolution. Also the pin is toggling every 60 microseconds. That means we have the same sampling frequency, which was prior to the oversampling. Let me change the voltage back to 1.1 volts, and capture the data again. We are now getting the maximum value of around 19,000, which is near 1/3 of the maximum 16-bit value. But note that the output data still has jitters, even at this resolution. Now this may be due to a lot of reasons, but I am assuming one of them could be the resolution. We will now see how to use even the higher oversampling ratio. Let's open the CubeMX again. I can only reduce the prescaler by a factor of 4 now. So I am going to use the oversampling ratio of 64, and to do so, I need to use the bit shift of 2. This will result in a resolution of 16 bits again, but now we are taking 64 samples instead of 16 samples. Alright, let's test the updated project again. Here you can see the output data has less jitters now, but the maximum value is a bit lesser than what we were getting before. It can happen as there are a lot of samples being averaged to get these values. Although the resolution is still 16 bits. Also note that the sampling time is the same, 60 microseconds. So we saw how the oversampling increases the resolution, and it makes the output more uniform. But it rescues the sampling frequency, therefore the frequency needs to be increased by the same factor, which is used for the oversampling. Let's take a quick look at the reference manual of the H750. Here open the ADC register map. You can see the ADC data register is 32 bits in size, therefore the oversampler here will not have restrictions like we saw in case of L496. Let's check out the oversampler section under the ADC functional description. As mentioned here, we can use the oversampling ratio from 2 to 1024. Even if we accumulate the oversampling results on the 16-bit data, we can reach up to 26 bits resolution with the ratio of 1024, without any bit shift. Storing 26 bits is still possible for the data register as it is 32 bits wide. We can also use the bit shifting to reduce the resolution as per our requirement. The rest of the processing will remain the same as we discussed in case of L496. Whatever microcontroller you are using, it will either have the data register 16 bits or 32 bits wide. So the usage of the oversampler will vary as per the width of the data register. Today we will look into the reference voltage. This is going to be a very confusing video, so pay attention to every detail. I will explain why this reference voltage is an important parameter in the ADC, and how to measure this voltage using the internal reference voltage of STM32. We will also see the availability of the reference voltage pin on different STM32 dev boards, and even if the pin is available, how to actually make it useful in our application. I will demonstrate the measurements on 3 different dev boards, the Nucleo F446, Bluepill F103, and the H750 based custom board. Let's quickly take a look at the different types of voltages we are going to see in the video. At first we have the VDD, and VSS. These are the main supply voltages. The VDDA is the separate analog supply, and it is used to power the analog circuits in the MCU. In almost all the STM32 devices, the VDDA is connected to the VDD. Next we have the VREF, the reference voltage. This is basically the voltage with which the ADC input voltage is compared, and then the digital value is calculated based on the comparison. For example, if the VREF is at 3 volts, an input voltage of 1.5 volts will result in the digital value of half the max value. In the low-pin package MCU, a separate VREF pin is not available, and it is connected to the VDDA itself. Whereas in some high-end MCUs, the VREF pin is a separate pin, and we can use it to provide custom reference voltage for our ADC. There is another reference voltage, VREF-int. This is the fixed internal reference voltage, which can be used to measure external reference voltage. The VREF-int has a fixed value, and it does not vary if even the main supply voltage is reduced. Before we proceed with the video, just make sure you have the reference manual, datasheet, and the schematic of your board. I will start with the Nucleo F446 first. Let's open all the required documents for this dev board. We will start with the reference manual first. Go to the ADC section, and here you will find a table named ADC pins. As I mentioned earlier, the VREF is the external reference voltage, used for comparing the ADC input voltage. The ADC input voltage cannot be outside the VREF limits, or else the data will be limited to these voltages itself. The VDDA and VSSA are the separate analog supply voltages as discussed earlier. Now we know that the VREF Plus is a separate reference voltage for the ADC, but it has some limits, and you can find these limits in the datasheet or reference manual of your controller. Here for F446RE, the VREF Plus can be between 1.8 volts to VDDA. Whereas the VREF Minus is connected to the VSSA, which is then connected to the ground of the MCU. Even the reference manual says that VREF Plus and Minus pins are available in the MCU, that does not mean that your board will have it. Let's open the datasheet to investigate it more. Here search for the VREF Plus, and let's keep going until we find something useful. Here you can see for the 64 pins package, the VDDA and VREF Plus are assigned the same pin. So basically these signals are interconnected, and hence we cannot provide a separate voltage to VREF Plus. Similarly, VREF Minus and VSSA are interconnected, and we already know that VSSA is connected to ground, hence the VREF Minus is grounded too. On a 100-pin package, we do have a separate VREF Plus pin, but the VREF Minus is still connected to VSSA. Having a separate pin simply does not mean that we can provide separate voltage to VREF Plus, but now we need to check the schematic to figure out how this pin is connected. By default in every board I have seen so far, the VREF Plus is always connected to the VCC, but after making some hardware changes, we can separate this pin. We will see this in the H750 dev board. Let's keep looking for the VREF Plus in the datasheet. Here you can see the ADC characteristics. This table lists all the conditions required for the ADC. The VREF Plus voltage can vary from 1.7 volts to VDDA. Whereas the VDDA can vary from 1.7 volts to 3.6 volts. Now let's look for VREF-int. As discussed earlier, VREF-int has a fixed value, therefore this can be used to measure the external reference voltage, or the main supply voltage itself. For the F446RE, this internal reference voltage is around 1.21 volts. The calibration value for this voltage is stored in the memory of the MCU during the manufacturing process. As mentioned here, the calibration was done for the VDDA at 3.3 volts, and the values are stored at these addresses. I am using Nucleo F446, which is a 64-pin package, hence the VREF pins are tied to analog supplies. Also, as you can see in the schematic here, the VDDA is connected to the VDD, the main supply voltage. So in the case of Nucleo F446, the reference voltage is always the same as the supply voltage. Therefore we will use the internal reference voltage to measure the supply voltage of the Nucleo board itself. Imagine a scenario where you want to use the ADC on this board, but the board is battery powered. As the time passes by, the battery voltage will drop, and so will the supply voltage. If the ADC is configured to always refer to the 3.3 volts, the ADC readings will be wrong when supply voltage drops below 3.3. Therefore it is always recommended to measure the current VDD, so the ADC reference point can be updated accordingly. As the datasheet shows here, the minimum sampling time required for the VREFINT is 10 microseconds. I have already created a project for Nucleo F446. Let's see the configuration used in this project. The system is running at maximum 180 MHz, whereas both the APB clocks are at 45 MHz. This means that the ADC clock is also at 45 MHz. I have enabled the VREFINT channel of the ADC1. I am using a prescaler of 8 to reduce the ADC clock, and the sampling time is set to 480 cycles. With the current setup, the ADC will take around 87 microseconds to convert the internal reference channel, which is more than 10 microseconds, so it is fine. Let's enable one more ADC channel, where we will supply the input voltage. Now we are doing two conversions, so enable the scan conversion mode, set the number of channels to 2, and configure the channel 0. I am going to use the DMA for multiple channel conversion. Make sure the DMA is in circular mode for the continuous conversion. Also enable the DMA continuous request. Alright, everything is configured, click Save to generate the project now. The VREFCalc retrieves the calibrated data from the memory. This is mentioned in the datasheet of the device. Also note that this data was measured with VDDA, at 3.3 volts, which is also mentioned here. Now inside the main function, we will start the ADC in DMA mode to read 2 channels. Once the conversion is finished, an interrupt will trigger and the conversion complete callback will be called. Inside this callback we will calculate the actual reference voltage using the converted value. This formula is defined in the reference manual of H750. After calculating the reference voltage, we will use it as the reference point to calculate the ADC input voltage. Alright, the project builds just fine, so we will load it to the board. But before doing that, let's make some hardware changes, so that we can vary the VDD. This jumper on the Nucleo board enabled it to receive the power supply from the ST-Link. When this jumper is connected, the VDD will be set to 3.3 volts. I will leave the ST-Link connected, but remove this jumper. Now I am supplying the power on the 5-volt pin of the board. Right now the supply voltage is set to 1.7 volts. Let's try to launch the debugger. Well, it did not work, as we know that the VDD needs to be higher than 1.8 volts. Now I am changing the supply voltage to 2 volts. The debugger has launched successfully. Let's run it now. You can see the VREF is being shown 2000 millivolts. Now I am going to vary the ADC input voltage. Also keep an eye on the ADC value. Now the input voltage is 1 volt. The ADC value is around half the maximum, and the voltage variable is showing 1000 millivolts. Now the input voltage is 2 volts, same as VDD. You can see the ADC value is at maximum 4095, and the voltage is also around 2000 millivolts. Now imagine if the battery voltage drops to 2 volts, and we do not measure the reference voltage. Our reference point is set at 3.3 volts. The ADC will still measure 2 volts as 4095, and our calculation will show this as 3.3 volts input voltage. Now I am increasing the supply voltage to 2.5 volts. The reference voltage is also changed, and the ADC will now measure the input voltage against this 2.5 volt reference. Therefore the ADC value has been reduced. But because we are setting the Vref as our reference point, our calculated voltage is the same as input voltage. Now we can measure the input voltage up to 2.5 volts. This is how the VDD affects the ADC, and therefore when using the battery to power the system, you must set up the ADC to measure the VDD. Note that the method we used is to measure the Vref, but since in Nucleo F446, the Vref is connected to VDD, we are getting the measurements for VDD itself. Now we will do the same in F103C8 blue pill. Let's open the manual and datasheet of this MCU. Let's start with the datasheet and search for the Vref+. Here you can see the Vre+ pin is available in a 100 pins package, but it is not available in 64 pins. It must be connected to the VDDA. It is also not available in a 48 pins package, and must be connected to the VDDA. If you do have a separate Vref+ pin available on the board, it must have a voltage between 2.4 volts and VDDA. The VDD also varies between 2.4 volts to 3.6 volts. Let's look for the Vref int. Here you can see this voltage is fixed at around 1.2 volts, but unlike F446, this MCU does not have a calibration data for the Vref int. Don't worry about it, as we will get the data ourselves. Here I have already created a project for F103C8. Let's check the Cube MX configuration once. Also note that the sampling time for the internal reference channel must be between 5 to 17 microseconds. Here I have enabled the Vref int channel in the ADC1. The channel sampling time and ADC clock is set so that we get the conversion time between the specified limits. In the main code we will simply read the ADC value for the internal reference channel. The board is powered with 3.3 volts right now, and we got the ADC value 1530. Make sure to call the calibration function once before starting the ADC. Now we will use this 1530 as a calibrated value for the internal reference voltage. Finally calculate the Vref using the calibrated value we just defined. The calibrated value we calculated was using 3.3 volts VDD, hence the 3300. To provide the variable power supply, we need to remove the 3.3 volt supply from the SD link, and then connect the external power supply to the 5 volts pin of the board. Right now the supply voltage is set to 2.5 volts. Let's debug this project. You can see the Vref is around 2400 millivolts. Now I am increasing the supply to around 2.8 volts. You can see the changes in the debugger as well. When the battery voltage drops, the VDD will also drop, and so does the Vref. As long as the Vref is above 2 volts, things will work just fine. We can use this measured Vref to calculate the ADC input voltage. So we saw the two MCUs so far. In both of them, the Vref pin was connected to the VDDA, which was then connected to the VDD. Hence we could not have a separate reference and supply voltages. If you take a look at the schematic of the H745 Discovery board, here you can see the Vref+ pin is separate from the VDDA. But there is a 0 ohm resistor connecting both of them, which is then connected to the VDD of the MCU. So by default the VREF of the board is connected to the VDD. If we remove this R66, the VREF pin will be completely independent, and we can provide a separate reference voltage for the ADC, while the MCU is still running at VDD. But removing R66 alone will not be enough on this board. Here you can see the physical VREF pin is not connected to the MCU's VREF pin. So we need to also close this SB20 connection to connect them both. Once both the changes are made, we can provide the external reference voltage for the ADC. Now I did not do it on this board as this is very expensive. But I did something similar on the H750 custom dev board. Here you can see the schematic of this board. The VREF pin is connected to the 3.3 volts, via this 0 ohm resistor R11. I removed this resistor, and therefore the VREF becomes open. We can then connect the external reference voltage on this pin. Also note that VDDA is a separate pin, which is connected to 3.3 volts, via the R34. Let's take a look at the datasheet of this H750 MCU. We will again look for VREF+. Here you can see the range for VREF+ is between 2 volts to VDDA. We should keep this in mind when providing external reference voltage for the ADC. If you want a lower reference, disconnect the VDDA from 3.3 volts, and provide external voltage for the VDDA as well. Now we will look for the VREF int. Here we have a typical 1.216 volts for the internal reference voltage. And there is calibration data for the VREF, stored in the memory as well. Alright, I have already created a base project for H750. Let's configure the ADC1 channel 3 in single-ended mode. This is where we will measure the ADC input voltage. Let me first fix the ADC clock issue here. The ADC is clocked at 75 MHz right now. Let's use a high prescaler so that the measurement will be slow. I am also enabling the DMA in the circular mode, so the conversion and transfer will take place using the DMA. Let's set a high sampling time for this channel, so that we do not interrupt very often. The internal reference channel is in ADC3, so we will enable it there. Let's configure this channel so that we get the sampling time higher than 4 microseconds, as specified in the datasheet. We will read this channel in the blocking mode, so no interrupt or DMA is needed. Alright, that is all. Click Save to generate the project. Let's define an array to store 2 ADC values. We will store the calculated VREF here, and the input voltage here. Now let's fetch the calibrated VREF data from the memory. Now inside the while loop, we will convert the VREF int channel of the ADC3. I am storing the value in the first element of the array. Inside the main function, start the ADC1 in the DMA mode. We will read the input voltage here, and the ADC value will be stored in the 0th element of the array. Once the DMA finishes the conversion, we will simply set this variable to 1. Now inside the while loop, first calculate the VREF voltage using the calibrated data, and the ADC value of the internal channel. If the variable is set to 1, we will use this VREF as the reference point to calculate the actual input voltage. That is all. Let's build and debug this project. This is the connection for this board. The board is powered with 3.3 volts from the SD link itself. Therefore the VDD is fixed at 3.3 volts. Although I am providing a separate power supply to the VREF+ pin. Let me adjust it to 2 volts. The Active Pro will be used to provide a variable input voltage to the ADC input. Let's run the debugger now. You can see the Vref is at 200 mV. Keep in mind that Vref is a separate pin here, hence the VDD is not being changed. It is still at 3.3 volts. Now I will vary the input voltage to the ADC. You can see the voltage value is updating according to the input voltage. Also keep an eye on the ADC value at the 0th element. This is the value as per the input voltage. You can see that at 2 volts, we have reached the full resolution. This is the advantage of using an external reference voltage. Say for example, if the sensor outputs the voltage between 0 to 2 volts. We can use the external reference voltage of 2 volts to get the full-scale resolution of 16 bits. You can see at 0 volts, we are getting the value around 1000, whereas at 2 volts, the value is around maximum 65,535. If you do not want to provide an external supply on the Vref pin, there is one more way to generate a fixed reference voltage. Some of the STM32 devices are provided with the Vref buff peripheral. It is used to set a predefined reference voltage on the Vref pin. We can enable the internal voltage reference here. You can see the pin VRE Plus is now configured as Vref buff out pin. You can even connect it to the sensor's VCC to power the sensor. But it is capable of providing a very small current, somewhat around 4 milliamps. We have only a few sets of voltages available here, so I am going to set it at 1.5 volts. Alright, let's generate the project again. Although we do not need to measure the Vref now, but I will keep the code same, so that we can see if the Vref voltage is generated as per the configuration. Let's debug the project. I have removed the external supply on the Vref pin and the 1500 mV you are seeing is generated internally. Let's vary the input voltage. You can see that the ADC value has reached maximum at 1.5 volts now. So we are getting a full-scale resolution at 1.5 volts. But still the Vref is not exactly 1500 mV. Let's do the calibration for ADC3 once. Let's call the calibration function inside the main function. The calibration mode is set to linear calibration offset, and the channel is configured in single-ended mode. Alright, let's build, and debug it again. Now you can see we are getting the reference voltage of 1500 mV. Actually the calibration is required for measurement, not the generation. So even if it is not calibrated, the voltage generated is still 1.5 volts. The error was simply there in the measurement of the Vref. Like I said earlier, since we are generating it internally, we do not need to measure it. So you saw how we can use the external reference voltage to reduce the reference point for the ADC input voltage. This can help us get the maximum resolution, even at the low voltages. Also for the devices, where a separate Vref pin is not available, we can reduce the VDD itself. Differential ADCs are used in applications requiring high precision, noise reduction, and increased dynamic range. Today in this tutorial we will see how the differential ADC can measure the voltage difference between the two inputs. The measured voltage by the ADC will be a difference between the voltages on its two inputs. Not all the STM32 devices support differential ADC, so I am using the H750 based custom development board. Let's take a look at the reference manual of this board. Open the ADC section and go to the differential inputs part. As mentioned here, in differential mode, the analog voltage to be converted is basically the difference between the voltages on two inputs. Even though the ADC is converting the difference between the voltages, the output data is still unsigned data. We will see how this works in a while. When the positive input is equal to Vref minus, or the negative input is equal to Vref plus, the output data is 0. Similarly, when the positive input is equal to Vref plus, or the negative input is equal to Vref minus, the output data is maximum. Here is the formula, based on which the output data is calculated by the ADC. Here you can see the image explaining how the output data is calculated. We saw in the previous video that the Vref minus is always connected to the ground of the MCU. Therefore I am taking the Vref minus to 0. Although we can vary Vref plus, but by default it is connected to the 3.3 volts. When the positive input is equal to Vref plus, and negative input is equal to 0, the converted value will be maximum, 65,535 in case of 16-bit resolution. We will write the code in a way that the voltage calculated by the ADC at this point will be positive 3.3 volts. When the positive and negative inputs become equal, the converted value will be exactly half the maximum. The calculated voltage at this point will be 0. And similarly, when the positive input is equal to 0, and negative input is equal to Vref plus, the converted value will be 0. The calculated voltage at this point will be negative 3.3 volts. Differential ADCs require specific conditions to function correctly. One of them is that both the inputs should be biased at half the reference voltage. In other words, instead of fluctuating around 0 volts, the signals should be centered around 1.65 volts. We should also consider the common mode voltage. This common mode voltage is the average voltage of two input signals in a differential system. This voltage only has a small range in STM32, and you can find it in the datasheet of the device. Here you can see the common mode voltage varies by only 10% from half the Vref voltage. So if the Vref is at 3.3 volts, the common mode voltage can vary from around 1.48 volts to 1.82 volts. When choosing the input voltages on both the differential pairs, make sure the average of both voltages lies within this range. It does not mean that it will not work outside this range, rather the result outside this range is unpredictable. In certain cases it might work, while in other cases it won't. We will also see this in a while. Let's start the cube IDE now. I have already created a project, and here you can see the clock is configured to run at maximum 480 MHz. Now let's go to ADC1, and I am configuring channel 3 in the differential mode. You can see the pin PA6 is configured as the positive input pin, whereas PA7 is the negative input pin. Let's configure the ADC now. I am enabling the continuous conversion mode, so the next conversion can continue after the previous one is finished. Let's enable the ADC global interrupt also. Alright, that is all. Click Save to generate the project. Let's define a variable to store the raw ADC value, and the voltage variable will store the converted voltage. Inside the main function, start the ADC in interrupt mode. But before that, let's call the calibration function to calibrate the ADC in single-ended mode. Once the ADC finishes the conversion, an interrupt will trigger and the conversion complete callback will be called. Inside this callback we will first read the raw ADC value. Then use this value to calculate the voltage. Here I want the voltage range to vary from positive 3.3 volts to negative 3.3 volts. This formula is taken from one of the examples provided by the ST. Alright, that is all. Let's build and debug the project. I have added both the variables in the live expression. I am using the Active Pro to supply the variable voltages on both the inputs. Here the A1 channel is connected to the positive input of the ADC, and the A0 channel is connected to the negative input. Let's run the debugger now. Let's supply 1.6 volts on both the inputs. The voltage calculated by the ADC is around 0 volt. The values are changing very fast here. Let's make some modification in the code. Instead of doing the calculation in the callback function, let's just set the variable is done here. And later in the while loop, we will check if this variable is set. If it is, then we will do the calculation here itself. And provide some delay so that the values do not change rapidly. Alright, let's debug the project again. Alright, the voltage is around 0 right now. Now I have increased the positive supply to 1.7 volts, while the negative is still 1.6 volts. The voltage variable clearly shows the difference in voltage is positive 100 millivolts. Now the difference is 200 millivolts. Now it is 300 millivolts. And now we have a difference of 400 millivolts. Now I am providing 3 volts to the positive supply, and you can see the difference is around 1500 millivolts. Note that at this point, the average voltage on both the inputs is around 2.3 volts, which is outside the common mode voltage range. Hence we are not getting accurate data for these inputs. Now the difference should be 1 volts, but we are getting around 1.5 volts. The average voltage of inputs is way higher than the common mode voltage, and therefore the value is inaccurate. Now both inputs have the same voltage, so the difference is 0. The average input voltage is very close to the common mode voltage range, hence we are getting correct data, but it is still not very accurate. Now the difference in the input voltage is 1 volt, and we are getting accurate data. The average input voltage is also within the common mode voltage range. So as long as the average input voltage is within the common mode voltage range, the ADC will measure the difference in the input voltages very accurately. It still measures the voltage outside the common mode voltage range, but the average input voltage should not be too far from the common mode voltage range. When both the inputs are set to 0, the average input voltage is too far from the common mode voltage range. Hence we are seeing a very inaccurate calculated voltage at this point. Let's try to calculate some negative voltages too. Now the positive input is at 0 volt, whereas the negative input is at 3.3 volts. You can see the calculated voltage is negative 3.3 volt. Basically the calculated voltage has the range from negative 3.3 volts to positive 3.3 volts. So you saw how the differential ADC measures the voltage difference between the two inputs. We should also take care of the common mode voltage range while designing the project. If you want to measure low voltages, you can use a custom low reference voltage. I have covered how to do it in the previous video itself. That is it for the video. I will make a video in the near future, covering the application of differential ADC, where we will measure readings of the strain gauge. You can download the project from the link in the description. Leave comments in case of any doubt. Keep watching, and have a nice day ahead.